Hi everyone, we're going to continue on with elimination reactions. Today I will be talking about the E2 reaction. So the E2 reaction is going to be a single step process. So we're going to have no intermediates. E2 stands for elimination by molecular. So remember the bi is where the 2 is coming from, and bimolecular just means that there are 2 substances that are part of the rate. So both the concentration of the substrate and the concentration of the nucleophile will play in the rate of the overall reaction. So let's look at a simple mechanism. So up here we have our substrate. So again, when you're doing these problems, you really want to think, is it on a primary, a secondary, a tertiary? And when E2 reactions happen, a lot of times an SN2 product will also form. There are some instances that we will look at, for example, the one that we will look at right now, where E2 will be the only product. But a lot of times, again, it's going to be a mixture of SN2 products and E2 products. When you have the SN1 reaction, remember the SN1 products and the E1 products, there will be the mixture of both of those. So when we're looking at E2, so looking at this carbon here, we have a tertiary carbon. We have a good leaving group. So bromine, remember, is a good leaving group. We have a strong base or nucleophile. So we would think that this would proceed via a SN2 reaction or an E2 reaction. The main problem that we have for an SN2 reaction, remember that we said for an SN2 reaction, we cannot have a tertiary substrate. And the reason for that is because we can't have this nucleophile really get in for a backside attack. So since that can't happen, this reaction is just going to proceed via an E2 reaction. So again, if you have a tertiary substrate with a strong nucleophile, it will proceed only E2. So looking at our elimination product, we have our elimination product right here. So again, we're going to think, okay, we have our alpha carbon. Think of all your beta carbons that you have. So it's going to be beta elimination. Again, we're removing a proton from that beta carbon. And then we will have our leaving group, and we will have our ethanol right here. So again, remember the main point here is that you would have to know, if you're given this problem, that this cannot undergo that SN2 reaction just because of that bulky substrate. So again, this is where chapter 6 is also going to come into play with chapter 7. So you really just have to think about every single factor that you're working with. When we look at the molecular orbital interactions in E2 reactions, so MO again is molecular orbital interactions in E2 reactions. So what we want to do, so E2 reactions, remember, are always going to be single step. So we have no intermediates that are going to be formed. So what must happen is our beta hydrogen, so the hydrogen that's being removed, must be anti-periplanar. You may also hear the term coplanar with the leaving group. So we have heard this term before. So remember, the anti-periplanar just means that it's going to be 180 degrees from each other. So an example would be something like this. So right here, these would be 180 degrees from each other. If we look at it in a Newman projection, so if we have something like this, so what that anti-periplanar means is our hydrogen here is the one that's going to be abstracted to form that double bond, and bromine here is our leaving group. So again, these would be anti-periplanar to each other, or 180 degrees from each other. When we look at this in a Newman projection, so Newman projections, if you need a little refresher on them, I definitely recommend kind of overlooking those in your notes and just let me know if you have any questions about them. So when we look at it in Newman projection, again, these are going to just be anti to each other. So the real reason that that has to happen is you have to think about your p orbitals. So remember that in order for a pi bond to form, the p orbitals must be parallel to each other. So if we look at this with the molecular orbitals, so we have our hydrogen here that we're going to be losing to form that double bond. We would have our bromine here. So again, when this hydrogen here is lost and this bromine here leaves, what happens is that puts our pi orbitals parallel to each other. So again, in order for that pi bond to form, they have to be parallel to each other. And this is the main reason, or really the only reason, why they have to be 180 degrees from each other in order to have the E2 product formed. Just because, again, E2 is a one-step process. So in the reaction, the two sp3 orbitals are going to rehybridize at the same time, and they will become those p orbitals of that new pi bond. So when we look at the rate equation for an E2 reaction, so I'm hoping that you guys are kind of already thinking around this process. So we know it's a single step. So remember that bimolecular indicates that we're going to have two different overall second order. So when it's overall second order, it's going to be first respect to the substrate and first respect to the nucleophile or the base. So you'll see nucleophile is going to equal base in the notes. So again, for an E2 reaction, we do need a strong nucleophile. And the reason that we need that strong nucleophile is because it is part of that overall rate equation. So if we were to use a weak nucleophile, the reaction would proceed too slowly. So let's look at some examples of E2 reactions. So we're going to look at only products that will result from that anti-periplanar elimination. So this is going to be where, again, Newman projections may come into play. Chair conformations may also come into play. So when we look at this first example here, so this base right here, you may not be familiar with. So this is tert butoxide. So what this is, it's going to be potassium. And then we have this bulky base right here. So since this part right here, this base right here is going to be really bulky, whenever you see tert butoxide, this is going to proceed only E2. And again, the reason it can only proceed E2, or the major products I should say, will be E2, is because that the group is just very bulky. So there are possibilities for some SN2 products to form, especially if it's on a primary carbon. But when we're looking at this substrate right here, we have this on a secondary, so our major products would definitely be E2. Again, if this was on an attack on a primary carbon, a backside attack wouldn't be too difficult, but the SN2 product still would not be that major product. So looking at this substrate here, again, we're going to think about our alpha, and then we have our beta carbons. So when we draw our products, remember you're eliminating a hydrogen from that beta carbon. So we have several different products that can form. So we have this product, we have the cis product, which would be, this would be our minor. And then we also have this product here, which would also be a minor product. So in order to see which would be the major or the minor, the Newman projections are really going to come into play here. So let's look at our trans product. So for the trans product, we're going to have something that looks like this. So when we draw the Newman projection, what the Newman projection is going to look like is going to be, so we have HA, we have CH3, oh, sorry about that. We have HB, CH3, and Br. So what we're doing is we're actually looking down this bond right here. So what happens is that our HA and our Br are anti-periplanar to each other. We know that this is the trans product because our methyl group here is on the opposite side of this methyl group here. So if they are right next to each other, then that would be cis. If they're far away from each other, that's going to be an indication that the trans product is forming. So again, when we remove minus HA and minus Br, this will allow us to form our trans product. If we were looking, so again, this is going to be pretty low in energy because our methyl groups are far away from each other, right? So this is a staggered conformation, so we're not going to have much energy really associated with this. When we look at the cis product, so for the cis product, what happens is we're going to have something that looks like this. So now we're going to be looking down at HB and Br. So we're really just kind of rotating that bond or that Newman projection, whichever way you would like to do it. So again, this is going to be for our cis product. So for the cis product, when we draw the Newman projection for this, we have HB, we're going to have HA over here, we have our methyl, so HB is going to be anti-periplanar or coplanar to our leaving group, which in this case is bromine. These methyl groups are right next to each other, so this is going to indicate that it's going to be cis to each other. When we look at the energy, so remember when we have staggered conformation, we still have those gauche interactions for that RR interaction. So this product right here, this cis product, would be higher in energy. So since it would be higher in energy, that's going to result in something that would be a minor product in comparison to that trans product. When we look at, let's look at the next example. So if we have something like this, so again, this reaction here is just going to be in that tert butoxide. So this is bulky, so we're going to think, okay, this is going to be E2 mostly just because this is on a secondary. Again, if it was on a primary, we would have some SN2 products present also. So this is our alpha carbon. We have a beta here and a beta here. So when we think about all the products that we can form, we have this product here, plus we have this product here. So when we look, this is going to be our minor product, and this would be our major product. So what we look at when we draw the Newman projection of this molecule, so we're looking down this bond right here. So C2H5, we have hydrogen, and we have a methyl. The back is going to be our hydrogen, our bromine, and our methyl group. So again, we have our hydrogen that would be eliminated, and our bromine are going to be anti-periplanar to each other. So after the removal of HBr, what happens is we are going to have a product that looks like this. Oops, sorry. So again, you'll see that these two methyl groups are going to be cis to each other. So since they're cis to each other, we know that this would have to be the major product. So again, like I mentioned, you may need a quick refresher on Newman projections in order to do these. And then this next example that we're going to look at, you may need a quick refresher on chair conformation. So of course, reach out to me if you have any questions with any of this as you're working through. So if we look at, so we have our bromine right here, we have our methyl right here. We're told that this is going to be done in tert butoxide. So right when you see this, you're thinking, okay, bulky base. So I know E2. It could be SN2 also if it is on a primary substrate. There could be some small percentages, which you guys will actually see in lab, the next lab that we're doing. So what happens is you have this right here is going to be a secondary. So what happens is that carbon-bromine bond is breaking as the elimination products are going to form. So we have our alpha here. So this is going to be a beta. This is going to be a beta. So we have two different products that we would think could form. So we have this product, or we have this product here. Again, just by removing that beta hydrogen. So in order to see which product would really form, we have to think about that chair conformation. So this is going to be equal to this chair. So what's going to actually happen is the molecule is going to flip to the less stable chair form. So when that happens, we have our hydrogen and our bromine, again, are going to be in the axial position, which has to happen in order for them to be anti-periplanar to each other. So since they are both in the axial position, again, this is going to be the least stable chair conformation, but this is what has to happen in order for this reaction to work or for the substrate to react. So when this happens, these two right here, hydrogen and bromine, are lost. And what we're going to do is we're going to form that double bond between that hydrogen and bromine. So that will show you that this right here would be our major product, and this product would not form. So again, just look at placement. So our methyl group is like carbon 1, then the double bond is going to be between carbon 2 and 3. So if we do that over here, we have our methyl at carbon 1 and then carbon 2, 3. So that's where you'll know to put the double bond between carbon 2 and 3. Let's look at another example. So the last example for today. So if we have something that looks like so our leaving group, again, this is going to be on a secondary. The reaction is done in tert butoxide, so we know our major products are going to be E2 products. We have our alpha carbon right here. So this is going to be a beta. This is going to be a beta. So we have a couple different products that could form. So our products that could form could be this product here, or it could be this product here. So looking at these, we have the Zaitsev product. So Zaitsev, remember, is just where that alkene is forming on the more substituted. So the alkene is more substituted. When we have the least substituted, this is called our Hoffman product. So again, least substituted, Zaitsev is going to be more substituted. So looking at these, which one would actually be the major product would be the Hoffman product. So the reason that the Hoffman product is the major product is just because this right here is going to be too sterically hindered. So again, the sterics are going to play a major factor in E2 reactions, and they can force a thermodynamically less stable, so the Hoffman product, to be the predominant species in the products. So please look over E1 reactions and E2 reactions. The next lecture, what I'm going to do is I'm going to summarize SN1 reactions and E1 reactions. I'm going to summarize SN2 reactions, E2 reactions, and then I will work through the thought process for a few different examples. I hope everyone's doing well. Have a great day, everyone.